In this example, we have a build-up beam and is constructed by welding two channels, which are C15 by 33.9, with two plates measuring 14 by 8.75 thickness on the top and bottom. They are separated by 6 inches. As a result, the centroid for the whole build-up beam is located in the center of this geometry, so it'll make it a little easier. One thing to note, the channel properties given here are for the individual channels, okay? And they are also reported in such a fashion that they are assuming an orientation. In this case, they're assuming that the X and Y are as these are presently represented. So if you were to given a problem and the channel was rotated 90 degrees, then your properties would be swapped. In other words, your moment of inertia for the channel, for the X, would then become the Y, and your Y the X. All right, so the first thing we're going to do here is to determine the moment of inertia about the X-axis. So we're going to break it up into 4 parts. So the 4 parts I choose are the plate 1, which is the top plate, the bottom plate I'm calling plate 2 or P2, the channel on the left is C3, and the channel on the right is C4. I then will indicate in a column the areas for each one of these, and the areas for the plates are simply the product of the base, 14 by 8.75, and the area for the channel is given as 10. So now I'm going to focus on determining the moment of inertia about the x-axis. So we're just concerned with where that centroid is located for the individual part off of that neutral axis, which is the x-axis. So if we look at what we call the D for it, on the plates, they're going to be from the centroid of that plate, okay, to the origin there. Okay, so we know that the depth of that channel is 10 inches, or I'm sorry, 15 inches, so it's going to be half of that, so that's 7.5, and that's going to be an additional half of the width of the plate, so 0.875, which results in 7.9375 for the D. Now the D for the channels is 0 because the centroid for those individual channels is located on the neutral axis. The next column over is simply going to be the product of the area times D squared. And then the next column over is the centroid, or excuse me, the moment of inertia for the individual parts. And we're going to use rectangle, which is 1/12 the base times the height to the third. Now the base here is going to be the 14, and the height on it is 0.875. And for the channel, we're given that as a property for that, and that's 315. So we add those two columns up, and that results in a moment of inertia in the x-axis of 2,180, reporting it to 3 significant figures. Next, we're going to focus on the radius of gyration, which is simply the square root of Ix over A. And that results in a value of 6.99. Now we're going to repeat this for the y-axis. So we're now considering the y-axis and the distance off the y-axis for these parts. And we'll notice that the plate is squarely on that y-axis. Its centroid runs right through it, so it has a value of 0 for D. Now, the channel has a different value because it is located off of that axis, y. And we're going to use the value of the x bar. Okay, so that's the distance from the base of the channel over to the left in this case. So we're going to add that plus half of b, and that results in 3.788. All right, then we're going to calculate a d squared. And then we're going to then calculate the moment of inertia for each individual parts. Now, the rectangle then switches here because this is about the y-axis. So now it's going to be 1/12 times, instead of it's going to be the height in this case, which is 14 cubed, okay, and then, I'm sorry, to the third, times the 0.875. So it's much larger because you expect it to be, because it's oriented in such that direction there. And then we're going to calculate the moment of inertia around the y-axis, which is, again, the summation of those I and 80a, or area times d squared. And that results in 703 inches cubed. The moment of, or the radius of gyration in the y results in 3.98.